Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a nice equation with complex numbers. If you're new to complex numbers, go ahead and check out my lecture videos and ask a lot of questions. I also have another channel that focuses on algebra, number theory, and trigonometry, and it's called Cyber Math, cyber with an S. Great, so let's go ahead and see how we can solve this equation in two different ways. The first method, so for our first method, we're going to use what we generally use for these kinds of equations. And that is replacing z with the general form, the standard form of the complex numbers. And what is it? It is z equals a plus bi, where a is the real part, b is the imaginary part, and I, as you should know, is the square root of -1. So when you square I, you get -1. Okay, I squared is equal to -1. That's something you should never forget. Great, now let's go ahead and substitute it. But what does z bar mean, right? The little line over there. It means the complex conjugate of z. So how do you define complex conjugate? This is the notation. And the way you define it is basically we're looking for another complex number such that when we multiply by z, we get a real number. When we add, we get a real number. And that can only be achieved by a minus bi. So you negate the imaginary part. That gives you z bar, which is the complex conjugate of z. Let's go ahead and plug everything in. We're ready. 1 plus z bar, which is a minus bi, plus I times z, which is a plus bi, equals z again, a plus bi. Now, to make things a little easier on yourself, maybe, you can subtract z from both sides first, factor out the z, and then proceed that way. No big deal. You're pretty much going to get the same thing. Because our goal is to get complex numbers on both sides and then set them equal to each other, and I'll tell you about the rule. But let's go ahead and distribute first. We're going to go ahead and multiply here and here. That's going to give us 1 plus a minus bi plus ai. And then now, remember what I told you earlier, I squared is -1, so that's going to give you minus b. And then that's equal to a plus bi. Now, the left-hand side needs a lot of work. We kind of have to put the real parts together. 1 plus a minus b. And then the imaginary parts, we can actually factor out the I, so we can write it as the quantity a minus b multiplied by I, and that's equal to a plus bi. Great. Now, when are two complex numbers equal to each other? Obviously, this has to be true all the time, right? So that means the real parts are equal. And once the real parts are equal, they cancel out. Imaginary parts have to be equal too. So it's very easy to prove that if a plus bi is equal to c plus di, then a is equal to c and b is equal to d. Okay? Just think about that and try to work it out. So this equals a, this equals b. Let's go ahead and write down what that means. 1 plus a minus b equals a. A cancels out, we get a 0. This means b is equal to 1. Great. And then from the second part, we get a minus b equals b. If you add b to both sides, plus b, some people like to show their work, that gives us a equals 2b. Yay, 2b or not 2b, that's the problem. If b is equal to 1, then a is equal to 2, because a is 2 times b. Make sense? So that means we got the answer, and the answer was z. We were solving for z, remember? And z was expressed as a plus bi in standard form. And by the way, a plus bi just happens to be the name of this channel, so hopefully you'll remember in case you forget. Okay? Now, since a is equal to 2 and b is equal to 1, our complex number, the infamous complex number z, is going to be 2 plus I. Is there only one solution for this equation? Looks like it, because we didn't find any a and b values that work in this scenario. So that should be a unique solution. But let's go ahead and take a look at the second method. And I like to present more than one, if possible, because it gives you different perspectives, and maybe you're going to like one of the methods better than the other. And of course, let us know in the comment section down below, okay, which one you like better. So the second method is going to use some properties of complex numbers. And what are they? Well, if you have a sum of two complex numbers, let me go ahead and write it down as a rule so you kind of know how that works, and conjugate the sum. Basically, the conjugate, or conjugate, not conjugate, the conjugate of the sum is the sum of conjugates. So in other words, you can write this as z1 bar plus z2 bar. Make sense? So the bar kind of distributes. And that works for addition, that works for subtraction, that works for multiplication, even for division this works. And actually, trust me, for division, it's a beautiful property. Okay? Now, And of course, there's another property that you need to know. If you take z1 and bar it twice in a row, that gives you the same number. Kind of like put your hand up and then turn it upside down and then turn it upside down again, right? Or flick a light switch on, off, and then on again. Same idea. So the conjugate of the conjugate is the number itself. And of course, the conjugate of some numbers equal themselves, and think about what they are. And the conjugate of some numbers are their opposites. Also think about what they are. So complex numbers are actually pretty interesting because they make up a structure which you can work with, like real numbers, actually even better. So let's go ahead and see how we can apply it to this scenario. So what we're going to do is we're going to stick to this equation, and then we want to conjugate both sides. How do we conjugate both sides? We put a big bar on both sides, and boom, that works. Why? Because if z1 equals z2, I guess needless to say, right? Their complex conjugates are also equal by definition again, right? You can easily prove that. Great. Now, let's go ahead and kind of expand on this, right? What does this mean? Well, first of all, we're going to have conjugate of 1, conjugate of z bar, and then conjugate of iz, and then equals z bar. Great. Z bar, double bar, is going to give you z, and 1 is a real number. So if you think about a plus bi turning into a minus bi with the conjugacy, right? That just means, that's just conjugacy, I don't know. Maybe write it like this. 1 is going to stay the same because real numbers do not change, okay? Because they're real. They're not, I want to say they're not complex, but they are. Because if b is 0, that's still a complex number. That's a different story. You get the idea, it's 1. This one is going to turn into a z, and this one is just going to turn into, didn't we say it works for product too? It does. So this can be written as the conjugate of I times the conjugate of z, but you got to remember the conjugate of I is negative I because it's an imaginary number, no real part, so it's just going to become minus I times z bar, and that's equal to z bar. How do we use that information? There's a couple ways to go about it. One method which I really like is to solve and substitute. So I'm going to go ahead and actually add iz bar to both sides, and then go ahead and factor out z bar. That's going to give me 1 plus I. And from here, guess what? You can isolate z bar. Z bar can be written as 1 plus z divided by 1 plus I, which is nice because then I can go ahead and use substitution because I have another equation. Remember, before we conjugated both sides, we had 1 plus, what was it? Z bar plus iz is equal to z. Now what I'm going to do, I'm going to go ahead and replace z bar with this, and hopefully that'll solve the problem. Let's see what happens. 1 plus z bar, which is 1 plus z, divided by 1 plus I, plus iz equals z. Our goal is to get rid of the fractions, put all the z terms together, and then factor out and divide. You get the idea? That's the recipe. So let's go ahead and we can also split it up, but I don't think that's necessary. Let's go ahead and multiply both sides by 1 plus I. I think that'll be like a good way to go about it. So that's going to distribute. That's going to give you 1 plus I. That's going to cancel this one out. That's going to give us 1 plus z. And then iz multiplied by 1 plus I gives us z times 1 plus I. Great. So you can kind of put together some stuff and factor that. But I'd like to do the following. I'd like to actually distribute this I here and then bring everything over to the other side. But here we're going to have 2 plus I. And then this is going to be a z. And then I'm going to keep the z and just distribute I plus I squared. That's just going to be I minus 1. And on the right-hand side, I have z times 1 plus I. Now I can go ahead and subtract everything that contains z from z times 1 plus I. So keep your work organized all the time so that you don't lose anything or you don't make mistakes. And now, again, we can distribute or factor out a z. Let's do that. Factor out, so you're going to get 1 plus I minus 1 minus I minus 1. You've got to be very careful here because you have this term in, you have this term in parentheses, so this minus sign needs to stay here. Okay? Cool. This is equal to 2 plus I. And now I can cancel these out, and the i's are going to cancel out. And guess what? We're going to end up with 1. How nice is that? If you did it differently, you would still get 1 from here. So what is that supposed to mean? It just means that z plus, not z, sorry. I thought it was a z. I can't even recognize my mind. 2 plus I is equal to z times 1, which is z. So what is z? If 2 plus I is equal to z, then $1 million question, z is equal to 2 plus I. Same as before, right? And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math, the Shorts channel, and A plus BI. And bye-bye.